ODE, forced or unforced? Unforced. The homogeneous part means that there's no forcing function. Okay, so this is unforced. True or false, a solution to an unforced harmonic oscillator is said to be the natural response or the free response. True. That is also called sometimes the steady state response. No, just kidding. The steady state response is the other thing. Because the natural response always dies out. Think about a harmonic oscillator on a spring. It's eventually going to come to a stop, right? So the natural response or the free response always dies out. And what's left is the forced response, and that's called the steady state response also. So what principle from chapter 1 is used to solve a forced harmonic oscillator equation? Linearity. It is not partial fractions. Linearity. It's the one where you have to solve the homogeneous equation, find the general solution to the homogeneous equation, then find a particular solution to the non-homogeneous equation, and then you add them together to get the general solution. Oh, good. Okay, so throughout the course, we've been discussing models for the harmonic oscillator. It's popped up several times. So far, we've only modeled harmonic oscillators that are subject to the restoring spring force and a damping force, which is usually friction. All right, so today, we're going to begin to study harmonic oscillators that are subject to external forces. It could be a force like shaking the table that the spring is oscillating on, or putting some external force where you're pushing the mass, so you're adding to the spring force or taking away from the spring force. Okay, so remember we started with Newton's second law, force equals mass times acceleration. That's how we developed the model for the harmonic oscillator. And we had some assumptions about how our forces work. We said the force of a spring is always going to be proportional to the displacement of the mass, and displacement we're measuring with y. So that's where our ky comes from. And then the damping is proportional to the speed of the mass, right? Because the faster it's moving, the more friction, the more damping we have. So the speed of the mass we represent with y prime, the derivative of position. So we have a force proportional to velocity. Right, so to include an external force, we add another term to the right-hand side of this equation. We're going to assume this external force is a function of time only, and we're just going to call it f of t. So some common forcing functions include constant functions, where you're just applying some constant force to the mass, or an exponential growth or decay function. You could start with a small amount of force and just make it bigger and bigger and bigger, or start with a great force and make it smaller and smaller and smaller. Or a sinusoidal function, where the force that you apply to the mass varies sinusoidally over time. Sometimes you apply a lot, sometimes you apply less. So our new equation, where you have an external force, is just the old harmonic oscillator plus f of t. And then we typically rewrite this just so that we don't have so many constants floating around. We solve for y double prime by dividing everything by m, and then rename the constants. So b over m and k over m and f of t over m. We rename all those things so we don't have so many constants. So we call b over m p, k over m we'll call q, and f of t, the forcing function divided by m, we'll call some other function g of t. Okay, so this equation here, this is a second order because it's got a second derivative. Linear. Linear, constant coefficient. All my coefficients are constants. Non-homogeneous, because that thing is not zero. That's what makes it non-homogeneous. Non-autonomous, because I have both y's and t's in there. Autonomous would be if you only had y's. So we call this thing the forced harmonic oscillator, or a forced equation, and we call g of t the forcing function. So if you just drop the g of t, if you just drop the forcing function, That's the corresponding homogeneous equation or the corresponding unforced equation. Okay. So we can just remove the forcing function and we can look at what would happen to this system if it was just left to its own devices without any forcing. And we solved the forced harmonic oscillator by an extension of the linearity principle that we first used to solve a first order linear non-homogeneous differential equation in chapter 1. So it's the same exact thing, except now we're doing it for a second order. First, find the general solution to the associated homogeneous equation. We'll call that y sub h. Then find a particular solution to the non-homogeneous equation via a lucky guess. And we'll call that y sub p for y particular. And then the general solution to the non-homogeneous equation is the sum of steps 1 and 2. So y general is just y homogeneous plus y particular. Okay, so a few comments. Solutions of a harmonic oscillator with damping and no external force. So solutions to the homogeneous equation, the unforced equation, always tend to 0 as time goes to infinity, right? Y homogeneous will always go to 0 because that spring will always die out. The damping force will always win. So the linearity principle says that the general solution, which is the sum of YH plus YP, Y homogeneous plus Y particular, means that as time goes to infinity, YH is going to go to 0, so YG is going to approach Y particular. Okay. And we call YH the natural response for the system. What happens when you have no forcing is called the natural response. And Y particular is called the forced response or the steady state response. So all solutions of a forced damped harmonic oscillator approach the steady state solution because the natural response dies out, leaving only the forced response. So this is sort of an example of what you might get. The natural response is to settle down to 0, and then you're just left with the forced response. All right, so we'll do one example where we solve a non-homogeneous second order equation, and then you'll have some practice. All right, so there were 3 steps, right? Step 1 is solve y sub h. We want to solve the homogeneous equation, which means just drop the forcing function. So I need to solve 2y double prime minus 4y prime minus 6y equals 0. All right, how do I do that? Yeah, so you can immediately jump to the characteristic equation. You could start with lucky guess and say, well, definitely I think that something that would solve this would be e to the st, not knowing what s is, because a function added to its derivative and its second derivative have to all be the same like terms so that I can actually add them together and get 0. But we saw that you could actually jump a few steps because it always comes out to the characteristic equation, which in this case would be 2s squared minus 4s minus 6 equals 0. Right, so you can, yeah, so if this factors, oops, 2s, s, and 3 and 2, so that would give you 6, and it needs to be minus and plus, yes. So we end up with s equals -1 or 3. So this is what gives me straight line solutions, right? I have e to the -t or an e to the 3t. Take a linear combination and you've got the general solution to the unforced equation. So y homogeneous is going to be k1 e to the -t plus k2 e to the 3t. Okay, so there's step 1. Step 2 is to find any solution, any particular solution to the forced equation. So 2y double prime minus 4y prime plus 6y plus 3e to the t. I think that was it. 3e to the 2t? Thanks. Minus 6y, okay. Okay, so what do you think? What could I guess? I need to guess a particular function. Something e to the 2t. Yeah, if I'm adding up some function and its derivative and its second derivative, they have to be all like terms in order to add them and just get a single thing, right? And my single thing is 3e to the 2t. So they have to all be some form of e to the 2t. So let's call it, I don't like using alpha because I get confused with my 2's. We'll call it a e to the 2t. Okay. So there's my guess. And I just have to figure out what a would make that equation true. So if y particular is a e to the 2t, then y particular prime, the derivative of that would be 2a e to the 2t. And y particular double prime would be 4a e to the 2t. Then I'm going to take my y particular prime, and my y particular double prime, plug it into my equation, figure out what a will make it true. So I've got 2 times y double prime, which is 4a e to the 2t, minus 4 times y prime, which is 2a e to the 2t, minus 6 times y, which is a e to the 2t. And I have to choose my a so that this all adds up to 3e to the 2t. All right, so I'm just going to do some multiplication, combining like terms. All right, so I have 8a e to the 2t minus 8a e to the 2t minus 6a e to the 2t equals 3e to the 2t. All right, so those go away. So if negative 6a e to the negative 2t equals 3, sorry, e to the 2t, not negative, equals 3e to the 2t, then negative 6a has to equal 3. The coefficients have to be equal. So you solve for a, and you get negative 1/2. So my y particular, a solution to the differential equation would be negative 1/2 e to the 2t. So my y particular is negative 1/2 e to the 2t. That's the step 2. Step 3 is just add them together. Add your yh and your yp, and that's your y general, your general solution. Yes, yes, it's a particular solution, not a general solution. Yeah. So my y general, my solution was k1 e to the negative t e to the negative 2 plus k2 e to the 3t. So there's my general solution. It's got two constants, right? Because it's a second order differential equation, it's got the two constants. And if I wanted to find a particular solution to an initial value problem, I would have to be given y of 0 and y prime of 0 to finish. And in fact, is this an initial value problem? No, okay, so I'm done. Not so bad, right? That's it. Okay, so your first one is an initial value problem, which means you're going to have to go a couple steps further to find the K1 and the K2.